Math 2414, Calculus 2, Section 9.2, Calculus with Parametric Curves. Video 2 of 9, excuse me, I've changed the wrong number. Video 2 of 9, Example 1. In the previous video, we discovered the formulas for calculating the first and second derivatives of y as a function of x if our curve is defined parametrically. dy dx was pretty easy. It's dy dt over dx dt. The second derivative, d2y over dx2, is a little less intuitive because you do take the first derivative's derivative, but then you divide it by dx dt again. And if you've forgotten why, then I'll refer you to the previous video for an explanation. In this video, we're going to do an example. We're going to take a curve defined parametrically, calculate some features of this curve, and then use the information to sketch the curve. Suppose c is defined by x equals t squared and y equals t cubed minus 3t. By the way, it would not be impossible to eliminate the parameter by solving the first equation for t and then substituting it. The problem is this equation implies a couple of things. Number one, x can't be negative because it's the square of something. So if we eliminated the parameter, there would be no graph to the left of the x-axis. Secondly, if we solve this for x, we would have to say t equals plus minus the square root of x, which would create two equations, one by substituting t equals the square root of x, and one by substituting t equals negative square root of x. As a consequence, when you have a curve defined parametrically, you should really be skilled in analyzing properties of that graph strictly from the parametric equations, although you can always entertain the idea of eliminating the parameter. I got four things in store. A, we're going to show C has two tangent lines at one point. Now, how can a graph have two different tangent lines at one point? You'll see. Well, I'll briefly tell you. Oh, we're going to find those tangent lines equations. When you define any curve parametrically, it's not like a standard function that goes from left to right and that y values just go up and down as you proceed from left to right. Because the x and y are independent of each other, the x can backtrack and you can have a curve that wiggles all over the place and even overlaps itself. At the point where it overlaps itself, there will be two tangent lines, one from the first time it goes through that point, one as it goes through the second time. You'll see that as we sketch this graph. Part B, find the points on C where the tangent line is horizontal or vertical. Well, we know we can find that by setting the correct derivative is equal to 0. C, determine where the curve is concave up and concave down. That's going to involve analyzing the second derivative, which we'll calculate using this formula. And part D, we're going to use all that information to sketch the curve. I want to do all this in one video, and I do have limited space. So as we answer these questions, I will probably put the results over here, erase it, and start over with the next part. Let's start with part A. Show C has two tangent lines at the point 3, 0. Well, if we're going to talk about the point 3, 0, we should probably figure out what the value of the parameter is at that point. So at 3, 0, we need the x to equal t squared. So we need t squared to equal 3, because that's the function for x. And we need the y to equal 0. T cubed minus 3t is equal to 0. Let's move this thing away for a moment. Write that a little bit better. T cubed minus 3t is equal to 0. Now we can solve both of these. This one's easy to solve. Just square root both sides. We get t equals plus minus the square root of 3. To solve this one, we would have to factor out a t, but that would leave t squared minus 3, and now we have all these factors equal to 0. So it's t is equal to 0 or t is equal to plus or minus 3. Well, that's good because we need values of the parameter that get us to the point 3, 0. And from analyzing the x function, we know that the parameter has to be t equals positive square root of 3 or negative square root of 3. Wonder what happens here at t equals 0? Well, we'll look at that in a moment. So, now we know the values of the parameter that get us here. At t equals 3, square root of 3, and at t equals negative square root of 3. Sorry, I'm having trouble writing today. At t equals negative square root of 3. Well, let's see what happens at t equals the square root of 3. In order to calculate the tangent line slopes and find the equations, we need to calculate what this derivative is equal to. So maybe we should start with that. dy dt, dy dx, excuse me, I'm all over the place here. dy dx is equal to dy dt over dx dt. Well, these derivatives are pretty easy. Our y equation is t cubed minus 3t. Its derivative is 3t squared minus 3. Our x equation is x equals t squared, and its derivative is just 2t. So now we have an equation that tells us how to calculate the slope at a given value of the parameter. Let's look at our values that we're looking at. At t equals the square root of 3, we have dy dt equals 3 times the square root of 3 squared minus 3 over 2 times the square root of 3. Again, we're just substituting the square root of 3 into the formula for dy dx. In the numerator, the square root of 3 squared is 3. 3 times 3 is 9. 9 minus 3 is 6. On the bottom, we just have 2 square root of 3. 6 divided by 2 is 3, so we have 3 over the square root of 3. And although I'm not opposed to leaving irrational denominators like the square root of 3, this one you should rationalize because of what happens as a consequence. If we rationalize the denominator by multiplying both sides by the square root of 3, we get 3 square root of 3 on top. On the bottom, we get the square root of 3 times the square root of 3. That's the square root of 9, which is just 3. The 3's cancel, and we're left with just the square root of 3. For purposes of sketching the graph, this is about 1.7. So what does this tell us? This tells us at 3, 0, one tangent line has a slope of square root of 3. This is enough information to build an equation. We can use point slope form, which I'll abbreviate PSF. Recall that point slope form is y minus y1 equals m times x minus x1. So we'll substitute x1 is 3, y1 is 0, m equals the square root of 3. Y minus y1, so y minus 0, equals the slope, square root of 3, times x minus x1, so x minus 3. If we distribute that, we get y equals the square root of 3 times x minus 3 times the square root of 3. So we have one equation of a tangent line at that point. Y equals the square root of 3 times x minus 3 times the square root of 3. For the other value of the parameter, at t equals negative square root of 3, well, let's be efficient. What's going to change when we put a negative on the square root? Not the numerator, because it gets squared and becomes positive, but on the denominator. So substituting a negative square root of 3 instead of a square root of 3 should give us the same answer except negative. dy dx is equal to negative square root of 3. And how is that going to change our equation? Well, it's not going to change the point, it's only going to stick a negative here, which means we'll have a negative in front of the x term, and double negative multiplied will give us a positive. So without too much ballyhoo, if you will, our other tangent line is y equals negative square root of 3x plus 3 square root of 3. Okay? By the way, if you're writing something down and I erase it too fast, you're watching a video. Pause it. Back it up. Watch it again. I would recommend taking notes though, because watching a video does you no good if you don't remember what you saw later. All right. Part B. Find the points on C where the tangent line is horizontal or vertical. This one's a little bit easier. Horizontal means that the y-coordinate stops. So we need to solve dy dt equal to 0. Well, dy dt is t cubed minus 3t. Didn't we already solve this? Excuse me, that is not dy dt. dy dt is 3t squared minus 3. That's the derivative of y. We solved y equal to 0, not dy dt is equal to 0. If we factor out a 3, that leaves us a convenient t squared minus 1. The only way this is going to equal 0 is if t squared minus 1 is equal to 0, and the only way that's going to happen if t is equal to plus or minus 1. Now we need to go ahead and check the vertical ones before we say here's where the tangents are. Because remember, to be a tangent line, vertically or horizontally, one of your derivatives has to be 0 but not the other. For the vertical tangent lines, we need to solve dx dt is equal to 0. This implies that, it's a pretty bad arrow, this implies that this derivative, which is 2t, is equal to 0. Well, this implies t is equal to 0. Well, that's good. That's a different value of the parameter than we got up here. We don't have both derivatives being 0 simultaneously, so we do have vertical and horizontal tangent lines. Now, where are the points? Because that's what we're looking for. Find the points. Remember, our parameters aren't points. They're values we put into these two functions to calculate the point. That means that when t is equal to positive 1, our ordered pair is what we get when we substitute 1. 1 squared is 1. 1 cubed minus 3 times 1, that's 1 minus 3 is negative 2. And when t is equal to negative 1, negative 1 squared is still 1, but now negative 1 cubed, which is negative 1, minus 3 times negative 1, oh, minus 3 times negative 1 is positive 3. Negative 1 plus 3 is 2. And at t equals 0, so this implies that the ordered pair is 0 when we substitute 0 here and there. So this means that we have horizontal tangent lines at the points 1, negative 2 and 1, 2, and we have vertical tangent lines at the points 0, 0. One thing I meant to do on the previous part, and I'm going to back up and fix it now, is make note at which t values these points occur. For example, 3, 0 occurred at t equals plus minus square root of 3. 1, negative 2 occurred when t is equal to 1. 1, 2 occurred when t is equal to negative 1, and the origin occurs when t is equal to 0. The reason I'm keeping track of the parameters is that when we sketch the curve, we need to know the orientation, which direction it's drawn out as the t values increase. So we do have to keep track of our t values. All right. Part C, determine whether the curve is, when the curve is concave up or concave down. Well, that's a matter of solving the second derivative being greater than 0 or less than 0. So we need to calculate the second derivative. The second derivative of y with respect to x is going to be the derivative with respect to t of the first derivative divided by the derivative of x with respect to t. That's just the formula that we got from the first video. Well, we need dy dx, and I've erased it. So let me just put it back over here for a second. I can recover it pretty easily. Dy dx was dy dt, so this derivative, which was 3t squared minus 3, over dx dt, this derivative, which was 2x. I'm going to need to find the derivative of this. Probably going to use the quotient rule. Let's start by finding the derivative with respect to t of the first derivative. So in other words, the derivative with respect to t of 3t squared minus 3 over 2t. Some of you might be thinking, let's split this into two fractions, and you could do that. But some of you need practice with your quotient rule, and you know who you are. All right, the derivative of the top is 6t times the bottom, 2t, minus the derivative of the bottom, which is 2, times the top, 3t squared minus 3, over the bottom squared. Let's simplify this. This is 12t squared. When I distribute the negative 2, I get negative 6t squared plus 6. So we get 6t squared plus 6, and it's all over 4t squared when I square the denominator. Make sure I didn't make a mistake there. Something feels a little bit off. And I don't think that's right. Bottom times the derivative of the top, minus the top times the derivative of the bottom. Yeah, everything looks good. We can reduce this by 2, by the way. Imagine factoring a 2 out of the top. That 2 being a factor is eligible to reduce with the 4. That would leave us 3t squared plus 3 over 2t squared. But that's not our second derivative. Our second derivative is this guy that we just found, 3t squared plus 3 all over 2t squared, over the derivative of x with respect to t. The derivative of x with respect to t is 2t. This needs to be cleaned up. Let's think of this as the quotient of two fractions by putting the 2t over 1. So we can flip and multiply. 3t squared over 2t squared times 2t over 1, times 1 over 2t. I'm going to reciprocate. It would help if I wrote it upside down. We get 3t cubed plus 3t squared plus 3 over 2t to the third power. Alright, so far what we've done is calculated the second derivative. Let's move it over here to the side because we're about to do some more work. Second derivative is equal to 3t squared plus 3 over 2t to the third. And we need to know when this is positive and when this is negative because that determines concavity. It might also be nice to know where it's equal to 0 because that would give us a possible inflection point. But if you think about it real quick, this fraction is never going to equal 0 as long as t is a real number. You square a real number, at the very lowest it comes out 0. So at the very least, this numerator is 3. No chance of this fraction equaling 0. But we need to figure out where the second derivative is greater than 0 and where the second derivative is less than 0. As a fraction, to determine when it's positive or negative, we can consider where the top is positive and negative, where the bottom is positive and negative. But the top of this is always positive. It's not going to determine the fraction's sign. The second derivative will be positive when the bottom is also positive, because the top's already positive. The second derivative will be negative if the denominator is negative, because the top's always positive. So in other words, to figure out where this second derivative is positive or negative boils down to figuring out where its denominator is positive and its denominator is negative. Well, if we divide by 2, we get t cubed is greater than 0 and t cubed is less than 0. And knowing that when you cube a positive, it's positive, and when you cube a negative, it's negative, this is only true when t is greater than 0. This is only true when t is less than 0. When t is greater than 0, the second derivative is greater than 0, which means this graph is concave up when t is greater than 0. And when t is less than 0, the second derivative is less than 0, which means this graph is concave down when t is less than 0. So let's summarize that. Concave up when t is greater than 0, concave down when t is less than 0. This tells me that as we start on the graph, it will be concave down, and then after we cross where t is equal to 0, which is at the origin, it will be concave up. So it seems there's an inflection point at the origin, so to speak. All right, we've got all this information. Let's figure out what the graph looks like. I know this video is going pretty long. I'm going to bet, I'll check here in a second, that it's already ventured past the 15-minute mark, but it had 4 parts to it, so what do you expect? How about the 20-minute mark? We'll wrap up this video in just a moment. I don't like videos going this long, but this example merits it. Plus, it's Calculus 2, the end of Calculus 2. All right, let's sketch the curve. To sketch the curve, let's start by plotting the points that we already know. Notice that the points we talk about all have non-negative x values. Well, we already knew that because the x never had a chance of being negative in the first place. That means when I sketch this, I need no room over there. The rightmost x value of interest is 3. That doesn't mean we don't have to go beyond 3, but we need to get to at least 3. We know at 3, 0, our time, this happens 2 times. when the time is negative square root of 3 and when time is the positive square root of 3. So our graph's going to have to cross through that point twice. We know at time equals 1, we're at the point 1 comma negative 2, which is down here. So here's time equals 1. And at time equals negative 1, we're at the point 1 comma 2. So we hit this point before we hit that one. And at the origin, we hit the origin at time t equals 0. So in order, we have to go through this point, this one up here, this one over here, this one down here, and then this one. I can kind of start seeing a loop to it. But let's get a little bit more shape to this graph. Starting with the tangent lines from part A. At part A, we have 2 tangent lines. And really, since we know the point they go through, we really only have to focus on the slope. Square root of 3 is about 1.7. So to kind of get an idea of where the tangent line is with the positive slope, we would go over 1 and up about 1.7. 1 to 1.7 is about there. So we have a tangent line here. But we also have a tangent line at the point where the slope is negative square root of 3. To draw a slope of negative square root of 3, we can run 1 and rise negative square root of 3, which is about negative 1.7, right about here. So tangent line there. We also have a horizontal tangent line at t equals 1, a horizontal tangent line at t equals negative 1, and a vertical tangent line at t equals 0. So remember, these tangent lines are approximating the slope of these points. When we start out the graph, before we hit t is equal to 0, we're concave down. So we're concave down before we hit here, and once we hit there, we're concave up. So I think I'm ready to sketch this. This graph comes in, is tangent to this line at t equals negative square root of 3. Next stop is up here where it's tangent, horizontal tangent. Then I got to go to the origin where I have a vertical tangent. Then down here at t equals 1 where I have a horizontal tangent. Then back through this point again when time equals positive square root of 3 where I'm tangent to this other line. And it kind of looks like a fish. I could draw a little eyeball on it. Little mouth, maybe a couple of... Okay, that's not part of the graph, I just felt like drawing it. Alright, so does everything work? Well, we have all the tangent lines that we need. The 2 tangent lines whose equations we have at the point 3 comma 0. We've got the horizontal and vertical tangent lines where we predicted. The graph does start out concave down when we come through negative time, and when we hit 0, the concavity switches, so we could argue that at the origin there's an inflection point, and it's concave when it's supposed to be. Alright, so that was a tricky graph. Actually, it wasn't that tricky. It's not difficult, it's just a lot of information to process. And I'll be honest, this is a simple graph. You should see some of the weird ones.